Hello everyone, welcome back to my channel, Cardamom Mousery. Today we are finally going to be getting to part 2 of this Fancy Mouse Genetics Guide, specifically on color genetics. I did record all of this previously, but for some reason it's not letting me upload them. Not sure exactly what's going on with that, still working out this whole technology thing, learning as I go, but we're good. I'll just re-record it for you guys. Maybe try out a slightly different technique, see if I can get it to work this time. But with that said, I do at least want to get this information out to you guys, even if it takes arguing and fighting with technology a little bit to do so. So without further ado, let's get back into it. Real quick as a recap, we went over the A locus last time. And now we're going to be going over all of these other loci. And these are all the most common color loci that we see in the Fancy. The A locus, as we talked about last time, controls the distribution of yellow and black pigment. So it controls how much and where on the mouse we find eumelanin and pheomelanin, which is black and yellow pigment. And our most dominant was dominant yellow, which was the most vibrant and intense of the A locus genes. And then we had AVY, which was brindle. And then we had agouti, wild type, tan, AT. And then we had A for black or non-agouti. And we had AE, extreme black. So those are all the most common A locus genes or alleles that you'll see in the Fancy. And all of these other loci will act on this base distribution of pigment and dilute those colors in various ways. So, without further ado, let me just make sure I'm on the right layer. Yes, I am. All right, sweet. We are ready to get into it. So, on we go to the B locus. Now, the B locus is lovely. It's quite nice. It is the locus in charge of brown dilution or chocolate. And actually, it's not really a, dilution gene in the way that some of the other genes dilute, because as you see up here in the eumelanin section, eumelanin is both black and chocolate pigment. So chocolate's not a diluted version of black, it's its own pigment color. Just a different kind of eumelanin, basically. But on this locus, we have the allele uppercase B, which is wild type, and I have a little black self here, and all of these other non-agouti, undiluted wild-type versions all just have a black self, which is what non-agouti means. So if you ever see non-agouti anywhere, that's just another term for black self. So, we've got that as our base example. This is basically my version of an unmutated, unchanged, just normal mouse. It's basically if we took our A base variety, and then had no dilution or fancy genes. But then the mutated genes, and mutated genes are any of the genes that are different than wild type. So they're the genes that might mutate randomly, and because they're not in the wild, and they're in the fancy instead, we propagate them, and we keep the mutation around. So these are the non-wild mutated alleles, compared to the classic wild type. But here, we have BC. I might have this spelled wrong. I can't remember. It's either Corvidan or Cordovan. If anybody knows, leave it in the comments and I'll write in the description. But we have Corvidan chocolate, and then we have chocolate. Now these two are basically the same in effects for all intents and purposes. There is a slight difference. Corvidan brown is richer and warmer. This is the brown that we suspect we have in the Fancy, especially in show lines that are, nice with that rich pigment. But chocolate's also possible. People suspect maybe it's in feeder lines or other things. But typically, when people have chocolate, they'll just write B. Very few people ever write BC, Corvidan brown. We just write normal B. So, it's pretty simple. Very chill locus compared to the A locus. Just changes black pigment to chocolate. Actually, effect on yellow. Didn't go over that yet. So, eumelanin gets turned to chocolate. Pheomelanin, yellow pigment, has little to no effect. So it doesn't change much at all. So, for example, if we had this black tan right here, and it had chocolate dilution, or it was homozygous for chocolate, because as you can see, these are lowercase, so you need 2 copies for it to express. So if we had 2 copies of chocolate on this bad boy up here, then the top, that black eumelanin, would turn to chocolate, and this lower tan portion, the pheomelanin, would just stay yellow. Nice and vibrant. So, oh, and like a dominant yellow, it would just stay yellow. You wouldn't even be able to know that this mouse was chocolate if it had chocolate on it. So that kind of information is handy to have. That means you might get, if you breed a dominant yellow to another mouse, you might get chocolates out of the litter when you weren't expecting them. Next up is the D locus. And this locus is the blue locus. I love this one. Of course, uppercase D, the dominant wild type allele, is not a goody. It just basically means that it's not going to be diluted at all. And lowercase d is our mutation. It's our allele that actually does stuff on this locus, and that's blue dilution. And it dilutes black pigment to blue and yellow pigment to straw. And straw is actually quite lovely. I don't know how everybody in the fancy feels about it, but I personally really enjoy it. So you see this mouse up here, this is a blue tan. So it's a good example of blue dilution on both eumelanin and pheomelanin. So blue dilution dilutes black to blue like this, and then it dilutes yellow or tan to this straw color. It's more like a creamy, soft color. And if you compare this little dude to this tan over here, you can see like the intensity of the 2 colors, very different. So blue's almost like a pastel version of whatever color. A dominant yellow with blue dilution would become a straw, so it'd be fully like that creamy yellow color instead of the bold yellow color. Brindle would be a blue brindle, agouti would be a blue agouti, and then of course the blacks would be blues. Fun fact about blue dilution, actually, to help you understand the function a little bit better, but blue dilution is not actually a pigment. If you remember up here, eumelanin is black and chocolate pigment. Nowhere does it mention blue pigment. And if any of you guys are animal nerds, you'll probably know this, but blue pigment is extremely rare in nature. Most of the things we see that are blue are actually structural. The color is caused by the way that light reflects through whatever object it's shining through. So think like the ocean or the sky. They're not actually blue, but the way that the light reflects off of the particles leads to it looking blue. It's the same thing with pretty much all blue animals. I think there might be 1 or 2 exceptions. I can't remember them off the top of my head, but like all of your mammals especially, your cats, your dogs, any animal that has blue dilution, it's going to be structural. So on each strand of hair, pigment, black pigment, will actually clump, and then light will reflect off of it. And that's not that's not exactly what it looks like, but conceptually, just to help you understand it. So yeah, it's a structural color that is caused by the way that light reflects off of the individual hairs. And another fun fact for anybody who's breeding them and wants to like get good blues, one of the common faults in blues, if you're breeding for show type, is mealiness. And this is where like the tips of the fur almost look white or clear, and it creates kind of this mealy look on the mouse. They almost look like a roan when they're not a roan. And what causes this is actually when the pigment clumping happens intensely at the base of the hair. And this leaves very little pigment in the top, and since that part of the hair is almost clear, it makes it almost look like it's white at the top, and it gives it that mealy look. So when you're breeding for blues, you want to breed for even distribution, so that you don't end up with like a white tip at the end of the fur. Just a fun little look at what causes it, because especially if you're breeding for show, understanding the structure of the dilution is very helpful. But that's represented by a lowercase t again, and it's pretty dang fancy. And next up, we are on to the E locus. Alright, so the E locus is actually, it's one of my favorites. This is the locus of recessive yellow, and you might be wondering what's up with the E. That's because this locus is also called the extension locus. Now the reason for that is because it is known as an extension of the A locus. And as you can see here, our uppercase E, our wild type, non-agouti, just black self, unmutated. But the E, recessive yellow, when homozygous, gives us a recessive yellow when on top of black self. It acts on the A locus to make black pigment into yellow. And of course, some of y'all might be looking at this initially and being like, what? I thought the whole purpose of the A locus was, deciding where eumelanin and pheomelanin was. How can this weird little locus, the E locus, change where the yellow pigment is? Because it just took a black mouse and made it yellow. What? And this is where it gets really fun, because you're right, that is weird, but it's because the E locus is that extension locus, and it acts directly on whatever the A locus leaves it. And you can basically think of it like recessive yellow will look at anything the A locus leaves it, and it will look at any of the black pigment that the A locus leaves it, and it'll be like, nah, I don't want you here, and it will turn off the black. So it's not necessarily changing the distribution of the pigment so much as it's responding to the distribution that the A locus left and being like, I disagree. Let's get rid of that black pigment and turn it to yellow. And I'm not sure if I'm using the exact right terminology here, but I call it a leaky gene because the effects of the gene making black pigment into yellow get stronger over time. And what I mean by this is, you may have noticed I drew in like soot on the back. Recessive yellows, when they're born, sometimes even almost look like they're going to be black. And then over time, they just slowly get more and more yellow. There's more and more pheomelanin with time. And that's because with age, the effects of this gene get stronger. And by the time they're about 6 months old, oftentimes most of the soot and the black pigment that's been lingering is just gone. But as pups, many of my recessive yellows have a very dark line of soot on their backs, almost to the point where they look umbrous, which is a gene we'll get to another time. But yeah, so that's how you can remember recessive yellow. It's a very fancy gene. We love it. And it helps us get yellows. And actually, while we're talking about that, I don't know if I mentioned this, but both dominant yellow and brindle are prone to obesity, which you can select away from it with some work, but they're just naturally inclined towards it, and it's pretty hard to avoid. So all of our beautiful pheomelanistic yellows come with that really sad negative of obesity, but recessive yellow does not, which gives us the opportunity to have that beautiful pheomelanin without the obesity issues, which for me is amazing. I love yellow mice. I love the look, but I do not love the obesity. So that is why I personally keep recessive yellows, just because I've had brindles before, and it wasn't worth it for me as a breeder to work with the obesity issues. I wanted to focus more on the temperament and the color than I did on maintaining just the basic health. And with the brindles, it was a fight to get them to that point of being like, normal weight. So these guys just work a little bit better for me. There are some breeders who do well with them, though, who love them enough to put in the work. So brindles have a place. They do. And so dominant yellows have been around for a really long time. They're not very common here in the United States where I'm at, but they are much more common in Europe. And there's some beautiful lines of dominant reds there. On we go to the P locus. This one's pretty funky. I mean, they're all kind of funky if you think about it, but for some reason this one in my head is just the weirdo of the color dilution group. Of course, our uppercase P is our wild type, non-agouti. We've got our black self, and then lowercase p, when homozygous, gives us pink eye dilution. And this is the color that a black self will be when they have pink eye dilution. So it's kind of like this soft, cool gray color. The eyes will be pink, and actually, it dilutes the black pigment to dove. That's what this color is called right here. And then it has little effect on yellow, basically none. So it leaves yellow vibrant and sparkly and glorious, which gives you some very, very fascinating varieties. The color combination is very interesting. Because, like, imagine a black tan with pink eye dilution. This top black color diluted to that dove, and then the belly left that vibrant tan orangey color. That color with the tan on the belly, with the pink eyes, very striking. So pink eye dilution, for that reason, is, like, I feel like a lot of people have a love-hate relationship with it, because you can get those really amazing, striking mice that look super fancy and cool, but it also can do some really weird stuff. And that's because pink eye dilution is actually really close to the C dilutes that we're about to get into. And when you have two loci that are really close to each other, here I'll use this chromosome to demonstrate. Let's pretend that we have these two loci next to each other. We're getting really close. This one's the C locus, we'll pretend, and this one is the P locus that we just went over. When two loci are right next to each other, oftentimes when genes are getting inherited and DNA is being made, both of these can be like, oh, we're right next to each other? Well, I'm going to hold your hand and we're going to go together. So once you have pink eye dilution and you have a C dilute on the same mouse, they'll basically both be inherited as a package deal. And the mouse will pass them on together. Most of the time, loci, they are independent. So, like, it doesn't matter what you inherit on the A locus. It doesn't affect what you'll get on the B locus. Whatever alleles the parents have, they'll just pass on whichever. But when you have linkage like this, they actually do influence each other. And your brain might be exploding a little bit. That is exactly why a lot of people have a love-hate relationship with the C and the P loci, and especially when they're together. There are a few varieties that do include, like, intentional CP linkage, but most people avoid breeding mice that are pink eye dilution varieties and C dilute varieties together. They avoid it like the plague, because it can create a headache. It can create some cool stuff, honestly, but a headache, for sure. On to the C locus, though, so that you guys understand what we're getting into. C locus is probably, let's see, I don't even know which ones are my favorites, but I love the C dilutes. These guys are awesome. C dilutes dilute yellow and black pigment in various ways, and this locus, it's quite big, similar to our A locus. And once again, I wrote these in order of dominance for you. So let's go over each of these alleles. All right. First up is our classic wild type, non-agouti. This is an uppercase C, so it's dominant, which means that you need 2 copies of any C dilute for them to express. But fun fact about the C dilutes is that they actually will express together. So you can combine these basically, and you can get both of them expressing at the same time. This means that if you have like C and CE, it'll be a combo of those 2 varieties mixed together, which can get very fun. You can make some really cool stuff, but that's another reason that some people feel like the C locus is daunting. But I think once you understand how each one works individually, it makes sense. And it's pretty easy to kind of guess and figure out how they'd interact with each other. Eventually, if you're interested, I can make a video on the C dilutes and how they interact with each other and what varieties they make specifically. Give them a little bit more special attention, just because there is so much that you can do with the C locus. But for now, we'll just start by going over each one individually as if they were homozygous on a black self, so that you can see what their effect would be. First up, the most dominant is albino, and this completely dilutes all pigment to white. So eumelanin, pheomelanin, doesn't matter. It's going to be completely white. Eyes are going to be pink. There's no pigment anywhere. That's your classic mouse that you'll see in feeder bins. A lot of pet stores will have them specifically. And fun fact, even though they're pretty common in those settings, they're actually the easiest variety to get really good show type with. Like the big ears, the racy body plan, the long tail. All that stuff is easiest to get on the albino because you don't have to worry about breeding for color. So that's a fun fact about them. Next up is CE. This is extreme dilution, the next most powerful of the C dilutes. And this one dilutes black pigment to beige, which is this color up here, and yellow to white. So, as you can see, slightly less powerful than the albino, because instead of that white, fully diluted pigment, we still have black eyes, and the body is just this soft beige color instead. It's quite nice, very pastel. I'm a fan. I've got a few extreme dilutions myself right now. But if we had it on a tan, the top would be beige, that black eumelanin, and that tan belly, that pheomelanistic belly, would be white. So, that's CE, extreme dilution. Next up is CH, Himalayan. This is that fun temperature-controlled one we went over earlier. So the cooler parts of the mouse have more pigment, warmer parts have less, and this makes Siamese and other pointed varieties, because Siamese isn't the only variety of mice that have points. As long as you have one copy of CH, that temperature-controlled pointing effect will take place, but you can have CH with CE or C or CCH, and you will have points plus whatever effect that other gene has, which is really fun. So you can have pointed varieties that have like a beige base or an albino base, where they'll have like albino plus Himalayan is actually called a Himalayan, funnily enough, and they have points on the muzzle, and then they have like a white body still, and their eyes are more pink than a Siamese. Siamese have like ruby eyes, as you can see here. On an extreme dilution mouse, on a beige, they'll have points, and then they'll have this beige colored body. So it's a very subtle, I don't know, something about it feels elegant. The Siamese, the homozygous CH is probably the most striking. Their points are the most intense, with like the prettiest body gradation and coloration. And then on CCH, this is chinchilla dilution. And this is the weakest of all the C dilutes. It has a slight dilution effect on black, making it sepia, which is this kind of off color you see here, where it's not brown, but it's not black. It's like sad black. Although it's quite pretty, if I'm being honest. And then yellow or pheomelanin is diluted to cream or white. And you'll notice, like this one I just said, it dilutes yellow to white. CH does basically just dilute it to white, but because it's so much weaker, with selection and the other genes present in the mouse, you can actually get more of a creamy color. So you're able to kind of change up the appearance of chinchilla dilution a little bit more than with the other varieties. And you can actually select for the sepia color to be closer to black too. And that is how we get black foxes. Foxes, if you don't know, are when you have a tan mouse with a C dilute. Specifically, when the when the tan belly is turned to white, that's what we call a fox. So if that belly was white, this would be a fox. And the only way to get a black fox is with that chinchilla dilution. Because, this one, if you had beige, the top would be beige, belly would be white. That's not close to black at all. If you had Himalayan with a tan belly, belly would be white, because Himalayan dilutes yellow to white, basically. And then the top would be it would be like the Siamese with the points on top. Also not black. But in chinchilla dilution, since you can select it to be darker, that's as close as you're going to get to a black fox. So chinchilla dilution, if you want to get black foxes, that's your only option for C dilutes. But yeah, so those are all the C dilutes. Combined together, you get some really fun results. Oh, Himalayan CH with chinchilla gets you Burmese. And Burmese, they're like imagine a really, like a dark chocolate, or even just a chocolate with points, and then slightly cooler in color. And that's kind of what a Burmese looks like. So, very fun. The sea locus, yeah, basically it's fun. I'll show you guys down here when we do some mouse math, a couple different fun versions of Siamese. But here, let's get down here. I'm getting ahead of myself. Color this in. But all of these loci that we've gone over act on each other to get your end result. So all of the effects of each individual locus will basically compound on each other, and you consider them all together, and that's what gives us our end mouse. You can think of it like a recipe or a math equation, but a fun math equation. I was never a fan of math in high school, but this is math I can get behind. You add up all of the alleles on your various loci and their effects to get your end results. Now I'm going to go ahead and we'll see if I can put all of these together in one video. If I can, you'll see all of these fun equations in this video. But for safety, I'm at least going to record it in a separate section, just so that yeah, we'll see. I guess I'll at least go over this one right here for you guys. So let's say that I have ATA. These are both recessive on the A locus. AT is that tan, and if you remember, even though tan is recessive, that tan part, that pheomelanistic part, acts kind of like it's dominant. So even when it's only heterozygous, we'll still have that tan belly. And then we've got black self, so we know that the top part of this mouse is going to be black, and then its belly's going to be tan. And then if we take that black tan and we add pink eye dilution, this is homozygous lowercase p. If we add pink eye dilution, we know that pink eye dilution dilutes black to dove, and it doesn't dilute yellow or pheomelanin at all. So that means the top half of our black tan would be dove, and the bottom would be tan still. And you can see that here, we've still got that vibrant, intense, orangey tan color, and then we've got the soft pastel dove. And as I said, it's a very striking mouse. Seeing one in person, it's crazy, dude. 10 out of 10 would recommend. I don't breed them myself because I do not want to deal with CP linkage, but some people breed them, and they're fabulous. And let's go ahead, and either in this video or the next, you'll know better than I do. Let's get on to the rest of these examples for you. Give you some practice seeing these alleles and loci in action. Alrighty, guys, let's go ahead and finish this up with some fun little examples for you. So, let's start here. We're going over how the different fancy mouse color genes on their different loci add up and affect each other. And of course, as you remember at the very beginning, the A locus controls the distribution, so this is our base. This is our foundation. And then all of these other loci, all these other alleles will act on that foundation to give us our end result. So let's go ahead and see what that looks like in practice. Here we have lowercase a, that is non-agouti, or black self, homozygous. So we know that that will give us a black self base. Classic, simple, not really much pheomelanin to worry about. Plus, lowercase b, that's chocolate dilution, homozygous. And we know that chocolate dilution on top of black self gives us chocolate pigment. And if this mouse had any yellow, it would not affect the yellow at all. Now, we move on to this one. Once again, homozygous black self plus chocolate, but this time we also have blue dilution. So this is 3 loci instead of just 2, which is what we've looked at so far, is just 2 loci affecting each other. But 3 loci, that black self plus the chocolate, which would turn black self to chocolate, plus blue dilution, that turns black self to blue. So we get ourselves a lilac. This is chocolate and blue. It's almost like a purpley color. Not quite, but it's a combination of blue and chocolate. So these two, when they're both together on a black self, do kind of give you a mix of the two, which is really fun. So you've got like the blue color, which is more gray than lilac. Lilac's more purpley, and chocolate is warmer. Next up, we have black self again, homozygous AA, plus that blue, DD, lowercase dd, homozygous, plus EE, which, if you remember, is our extension locus, recessive yellow. So we know that black self, no pheomelanin to be seen. Blue on top of black self will dilute all of the black to blue. And EE, if you remember, dilutes black pigment to yellow. And if you remember this thing, blue dilutes yellow to straw. So if you remember, if we had like an AY and it had blue, it would be a straw instead. That wonderful blue tan up here, that straw belly. So we know that we have, because of the AA and EE together, we know that we have a recessive yellow plus DD gives us a blue recessive yellow, which is a straw. As you can see there, soft, creamy yellow. Oops. All right, and next up, AA again, our black self base. This time, no DD, no blue, and instead it's just EE, recessive yellow. So recessive yellow dilutes any black pigment that's left over to yellow. It says, no, sorry, black pigment, you're not allowed, get out of here, and it takes over. So this mouse is a recessive yellow, and as you can see, compared to the straw, which is the blue diluted yellow, it is very vibrant and warm. So that's a nice little comparison of those two. Now we're getting into some heterozygous stuff. This mouse is uppercase A, lowercase a. Uppercase A is a goody. Lowercase a is that black self again, plus chocolate, homozygous BB, gives us, and we'll think real quick, a goody is dominant, so it wins over black self, so we'll have an agouti mouse. And then BB, chocolate, dilutes black to chocolate, and it dilutes yellow to nothing. Has no effect on yellow. So that means that the ticking, because if you remember, our agoutis have ticking, each individual hair has both black and yellow. That means that the ticking will be chocolate and yellow, both those colors together. And that'll give us a cinnamon. Cinnamons are lovely. I don't actually have chocolate dilution in my colony right now. I used to a couple years ago, and cinnamons were always one of my favorites. I love them. They've got that nice chocolate color with that yellow mixed in. Very light and warm, especially compared to your classic agoutis. And then we've got another agouti, as you can see, dominant A here, with the black self that gets overpowered, left in the dust, plus DD this time. So before we had chocolate dilution, now we have blue dilution, lowercase dd, homozygous, and that gives us a blue agouti. If you remember, blue turns black to blue, and it turns yellow to straw. So that means that we're going to get a blue agouti with blue where the black was and straw where the normal yellow was. So you've got those two next to each other. Fun little comparison. And you can also look at the agouti in comparison, which is darker than the other two. Next up, here's that little star I talked about before. This is basically that placeholder, because here we have the dominant AVY, which is brindle, and it doesn't really matter, or we don't know what this allele is. Could be black self, could even be agouti technically. So we just leave that blank with a little star to indicate that we don't know for sure, but we at least know it's a brindle with lowercase dd. It's homozygous, which means this is going to be blue dilution on top of brindle, and as we said, blue turns black pigment to blue and yellow pigment to straw. which means that this mouse is going to be a blue brindle. Those stripes, which would normally be a goody, are going to be that blue color instead, and the body, which would normally be yellow, is going to be that creamy straw color. Next up is ATA. If you remember, tan is technically recessive, but that tan belly kind of acts like a dominant because that field melanin is just so powerful. So it's heterozygous with black self, which means we're going to have a black top with a tan belly, plus our blue dilution again, which will give us a blue tan. That lovely blue top where the eumelanin was, that blue dilutes that black to that blue. And then, man, that's a fun thing to say, blue dilutes black to blue. And then the belly becomes straw. And actually, right here, these three are an amazing example of why the A locus is so important. Because see all these guys? There's exactly one gene different between all three of them. Only one. They've all got a homozygous DD. This star could just be a normal lowercase a, not a goody like these ones. So they've all got that lowercase a, but then that one single allele on the A locus is different for each of them, and the result is that different. That massively different. These guys are all in completely different categories of varieties. So that's why I emphasize the importance of the A locus, because my guy, it's powerful. Knowing where that pigment is distributed is such an important part of breeding, and knowing what you're going to get. Anyways, on we go. Once again, we've got the heterozygous tan, so we're going to have that tan belly, and it's paired with just a black self. So it's going to be a black tan with BB, which is our chocolate dilution, homozygous recessive, so the top's going to be chocolate where the black pigment would be, and chocolate doesn't really affect yellow or pheomelanin, so we're going to get that lovely tan belly. Chocolate tan. Now we're going to have a little bit of fun with our C dilutes here. The C dilutes, they always make it fun. This is a whole 4 loci considered. But here we've got our classic black self, homozygous, lowercase a, plus, and right here, this gets weird, this is a heterozygous pairing. Uppercase B, if you remember, is the wild type on the chocolate locus, or the B locus, and it's next to our little recessive chocolate. But we need 2 copies of this chocolate for it to express. Since we've got this wild type gene, that means that even though this mouse carries chocolate, it will not be chocolate. So this mouse is not chocolate. We at least know that. Same story here with our blue dilution. It's got that wild type gene that's overpowering our sad little recessive here. So this mouse will not be blue. It will not be chocolate. But we do have homozygous CHCH, which, if you remember, is that wonderful temperature control gene up here. When it's homozygous, we get the wonderful steel point Siamese, which you have seen drawn quite a few times. If you can't tell, I love Siamese. I think they're so cool. That's a Siamese up there, and we've got this lovely Siamese here. And as you can see, even though the end result is a Siamese, there are a few genes it carries that we didn't see expressed. The end result was basically just phenotypically, all we could really tell is it was a black self-based Himalayan, which gives us that seal point Siamese. But this just goes to show that recessives can hide under anything, including diluted varieties. And below, this one, another good example of how important even just one allele can be. Because we've got our black self-base, lowercase a, this one right here is once again dominant, and it's our wild type for chocolate, and it overpowers our sad little recessive. But over here, instead of having that wild type D, we have both of our lowercase d's, both of our blue dilutions present. It's homozygous, which means blue dilution is present. And we know that black self with blue dilution will just be a blue. Now, if we add on Himalayan, a homozygous, which would normally give us that Siamese with points, we're going to have a blue mouse that has the Himalayan, which means blue point Siamese. So that blue will show up in the points where we still have pigment, and the body of a blue point Siamese is going to be more of a cool, soft pastel color than the seal point Siamese, which still has that warmth. But the blue dilution kind of takes that warmth away. They're very pretty. I love them. And as you can see, guys, that was one gene different. A singular gene. One allele. All we did was change that wild type D to the recessive so that it was homozygous for blue. And that single allele gave us two completely different varieties. Sure, they're both Siamese, but the color and the effect and the overall aesthetic of the mouse is going to be completely different. But because the A locus is the same, the distribution is pretty similar, at least. The difference isn't quite as striking with these two as it is with like these three right here. So yeah, this is why understanding your alleles and loci though is so important, because it just takes a tiny change for it to be different. But with that, we're done with at least this quick little example. The possible combos are endless when it comes to mouse genetics, especially the things we haven't gotten to yet. When you add coat and marking genes, it just gets crazier and more fun, in my opinion. You've got Merle, you've got Roan, you've got Splash, you've got Pied, you've got Variegated, you've got Banded and Belted, you've got Texels and Angoras and Hairless and Satin and Rex. It just gets crazy, man. It's fun. It's a good time. All the mice we discussed here today, just the tip of the iceberg when it comes to what's possible with fancy mice. So, without further ado, thank you for watching. I really appreciate you guys' interest, and I'm glad I was able to get this out there. Hopefully the editing program works for me this time. But if you guys have any questions based off of what you've heard today, or you have any subjects within this that you'd like me to go over, besides the coat, genes and stuff, which I will eventually get to, let me know. I'd love to hear a discussion going on in the comments. If you are another breeder, feel free to add any additional points of insight, any fun facts that you know about, or any corrections or like caveats you'd like to add to what I've said. Because this is just my way of understanding the subject, but we all have interesting and valuable perspectives to contribute. So thanks again for watching. I hope this was helpful, and good luck with your mouse adventures.